having introduced various plant models we frequently encounter, we frequently come across in industrial situations. Now, I think we are in a position to come to the complete feedback control system. So, that is why the subject which we are going to start from today concerns models of industrial control devices and complete systems which we are going to make using those devices. I will like to see the situation which we have seen, we revise the situation which we have seen with respect to the plant models. I will say that we have captured a model in a block diagram in this way, that the dynamics of the plant is described by a transfer function Gs. The input to the plant, let me say, is typically Rs, and the output is given by Ys. The controlled variable of the system is given by Ys. So, you see that Ys, the output, will always be equal to the transfer function Gs into the input to the plant or input to the block model Rs. So, this becomes a mathematical model in the transform domain for the plant, which is a system, which is a subsystem in the overall control system we are going to encounter. In addition to this, what else we have come across? Please see, we have come across these block diagrams also in our discussion. Let me assume that now I have two blocks, G1s and G2s. Rs is the input to this particular block and Ys is the output here. These are the two blocks here. Please see, if I have a variable xs in between, you know that Ys is equal to G2s into xs and xs is equal to G1s into Rs. So, that way if I couple these two equations, I get Ys is equal to G1s G2s into Rs. So, it means if two blocks are in cascade representing two subsystems of an overall system, I can multiply the two transfer functions to get the input output relationship in this form, that Ys is equal to the multiplication of the two transfer functions into Rs, the input of the system. In addition to these two, the other situation we have come across many times in my block diagram, if you recall, I have shown a circle in this form with these algebraic signs. I will be using this as an error detector or as a summing junction. The terminology being Rs is the signal here, Bs is the signal here, in that particular case E cap S, the signal at this particular point, will become Rs minus Bs, or let me say that if this signal is plus, naturally at this particular point I have addition of the two signals. So, this is the symbolic representation for me for an error detector or summing junction, where algebraic manipulations of two or more than two signals is required. The last point is, let us say that this represents a flow of signals. So, in that particular case, if I want to take off this signal for the purposes of feedback, please see, let me say that this signal is Ys. The takeoff has been represented in the block diagrams so far this way, that is, the signal at this particular point is taken off, so that the value of this signal, which is being fed back to some suitable point in the overall system, is also Ys. So, you will find that the total representation of the system will be a suitable set of these four basic elements of a block diagram. I repeat, a basic block, two blocks in cascade, and a summing junction and a takeoff point. The takeoff point, or you can even call it a branch off point, because from here the signal is being taken off for the purposes of feedback to other points. Now, before I go to a composite block diagram, one point I would like to mention, I think it is quite important, and that I take up with respect to a liquid level system. Only last time we have discussed this type of system, where the purpose is to control the height of the liquid in the tank. So, you see that the basic unit for me is this tank. You will recall my statement that if you are modeling a tank, you are going to get a model, a first order system, the personality of the tank dynamics being represented by system gain and time constant, and this is our model. This model we obtained last time only. That is, the height and the input flow are represented by a transfer function of this form. Consider another tank. The input to this particular tank is coming from the output of the first tank. In this particular case, same thing again, H2S over Q1S. Now the input is Q1S. It is represented by a transfer function given by this. This we have derived last time. Now I can put this total dynamics into a block diagram. Please see, QIS is the input. This is the transfer function of the system, so the output becomes H1S of the first block corresponding to the first tank. Here the input is Q1, but this Q1, I hope I can put it here itself. This Q1, as you know, is equal to P1 divided by R1, where P1 is the pressure at this point, the perturbation, the total pressure being P1 plus P1, where P1 plus P1 bar is the steady state pressure. So this Q1 is equal to P1 by R1. This is equal to, help me, I think you can write it this as rho g H1 by R1. So since in this particular case H1 is the output variable and not Q1, you see that the two are algebraically related by this equation. I can put this Q1 is equal to rho g H1 by R1, and if I multiply this with this, I get this as the transfer function. I need your attention please, I hope this is okay. I am simply eliminating this Q1 and writing this Q1 in terms of H1. You see that Q1S is equal to rho g divided by R1 into H1S. So substitute here. So H2S upon H1S will become R2 divided by R1, and the denominator being tau 2S plus 1. So that is why I have given this as the transfer function between H2 and H1, and these are the two blocks which represent the total dynamics of the system. Okay? I hope this is okay. Now if that is the case, please see, the point I want to mention is the following. The dynamics of this particular system, Q1 is the inflow and H2 is the controlled variable. It does not affect the dynamics of the first tank, and therefore, well, electrical terms we already know. In terms of non-electrical systems, I want to make it clear that it means that this particular subsystem does not load this system. So it is a non-loading component. This system connected in cascade does not load the system, and when the second subsystem does not load the first subsystem, then and only then the two transfer functions can be multiplied. Please see that these two transfer functions can be multiplied together to get a single transfer function H2S by QIS, provided this particular system does not load this particular system. I will make it clear with the help of another system equivalent where the two tanks are connected in cascade, and then I will come back to you and ask the questions if any. Now I take the same two tanks, but these two tanks are now connected this way. You find again that the flow out of the first tank is the inflow to the second. Similar situation but with a difference. And what is that difference? That difference will become clear from these mathematical equations. Please see, C1, again very well known to you, C1 dP1 by dt is the rate of storage in the tank 1 is equal to Qi, the input here, minus P1 minus P2 divided by R1. The second equation, C2 dP2 by dt is equal to Q1 minus P2 divided by R2. Look at this point please. P2 is the pressure of the second tank. However, this affects the flow or the dynamics of the first tank, and hence there is a loading effect. The loading due to the second tank on the first is there because of this variable, because this in the earlier situation, you recall this situation, this particular pressure was an atmospheric pressure at this particular point, and the second tank was not affecting this pressure, and hence the second tank was not affecting the flow out of the first tank. But in this particular case, this particular pressure is now the pressure of the second tank, and this affects the flow because the flow is given by P1 minus P2 divided by R1, and hence in this particular case the second tank loads the first tank. And therefore, when there is a loading effect, these two systems cannot be written in this form, that is, this as Qi, this as H2, this as G1, this as G2. This particular thing is wrong. This is not possible. The reason being that the two tanks or the two subsystems are not independent. The second subsystem loads the first. So in that particular situation, you will have to take this as a single unit. You cannot break this system into two subsystems. You will have to take this as a single unit. A simple exercise for you: these two equations, when suitably transformed into transform domain, Laplace domain, you get this as the mathematical equation. You get this as the transfer function of the system. And you will please note, though I made a statement that in a liquid level as well as in a thermal system, you will always get first order system. But however, in this particular case, we have got a second order system where the characteristic equation is given by a second order equation, that is, there is a quadratic lag, and this quadratic lag where zeta and omega n are appearing is coming because of the loading effect. As far as individual tanks are concerned, individual tanks are modeled by the time constant and the system gain. But if you put them in the non-loading fashion, you have got two time constants. In the non-loading fashion, the total transfer function is again a second order transfer function, but is represented by two time constants. When you take it in a loading fashion, in that particular case, please see the transfer function is a single transfer function where it is represented by a quadratic lag, that is, a zeta and omega n will appear as far as the personality of this particular system is concerned, and separating it out into two subsystems will not be possible because of the loading effect. So in my block diagram representation, it is just to make this statement: whenever in my block diagram I come across this situation, this is R, this is Y, this is G1, this is G2, it is implied, I may not explicitly say again and again, it is implied that this G2 does not affect or does not load G1. Please help me, if there is a loading, how can you help out? You see, you can help out by putting a suitable buffer in between. Electrical buffers, amplifiers, op-amp circuits, you already know. You can have a suitable pneumatic buffer as well. You can have a suitable hydraulic buffer as well, depending upon the type of system we are working with. So I at this stage will not like to go to the hardware details as to how to install or how to interface a buffer amplifier, a buffer in between the two units. I will simply like to make this statement that in overall block diagram, whenever I have two cascaded blocks, it simply means that either the loading effect is not there, if there it is negligible, if not negligible then I have already put suitable buffering effect in between so that the two transfer functions can be independently taken. If it is not possible, in that case the two subsystems have to be clubbed into a single system and they will be represented by a single transfer function only. Okay? This is a very important statement, because as you will see, when I come to the overall closed loop block diagrams for feedback control systems, you will have to take into account, when you take up various devices and interface them to make a total system, you will have to take into account this loading effect to get an appropriate mathematical model for this system. Okay? So I just now revise this. The 4 points will be for me like this. In a single slide, let me put it this way: a G transfer function, R and Y, two blocks in cascade. There will be hardly anything different than these four basic elements. This is R, this is Y, with the assumption that there is no loading effect. There should be a summing point plus minus R B, it is R plus minus B, and last point, let me take this Y signal and there is a takeoff. If there is a Y here, there is a Y here. I will say that when I give you block diagram representation of a total feedback control system, you will hardly come across any element other than these 4 basic elements. Okay. With this introduction, I can now probably go to the overall feedback control systems, and I will first of all like you to review what we have done earlier. And wherever you find that you are not remembering anything, please do raise an alarm, ask a question, I will revise that concept. Otherwise, the total block diagram which I am going to give you, we have already done. Okay. So, the very first element in this block diagram I put as YR, the standard symbols. I have already given these symbols earlier. YR is my command signal. Okay. This command signal can be suitably transformed to a reference signal R. By suitable transformation, I mean making it compatible with the feedback signal. Okay. And the elements in between, I can say reference input elements, and I call this as AS, the transfer function. Okay. This is sort of revision coming to you. Now, here let me say is an error detector or a summing junction. This is plus here and this is minus here, let me say a negative feedback system, a general basic structure I am taking. So, let me say that the feedback signal coming is B. Okay. Now, this R minus B is the net signal which I had symbolized as E cap, and I had named this E cap as the actuating error signal. Now, what is this actuating error signal doing? This actuating error signal is going to DS, the controller transfer function, okay, the transfer function of the subsystem which is going to control the manipulated signal to the plant. The output of DS we had represented by U, the control signal. After this U, we had taken a transfer function and GA was the symbol reserved for this. Let me now put S as the variable. GAS is the actuator transfer function, which is the power element of the system, which is the muscle of the overall control system, DS being the brain. Now, this GAS, after this I took the variable as M, which is the manipulated variable, which is the power signal given to the plant. Let me take it here. Okay. Now, let us say at this point I symbolically I said that let me assume that at this point, though it was made clear to you that disturbance can occur anywhere all through the block diagram, but symbolically I had taken this way plus plus. W was reserved for the disturbance signal. Okay. So, the disturbance is entering into the system through this particular at this particular point, and now after this I had taken the plant transfer function. GPS was reserved for the plant model. The output of the plant is your controlled variable, and this is being sensed through a suitable sensor signal HS. Suitable sensor signal HS. This is being sensed this way. Did I miss anything? Please help me. In this particular case, YS, I will like to project it this way. Y is the output signal, this is the sensor signal. Now, the thing which I have left is that there may be an indirectly controlled signal and it is being manipulated through indirectly controlled variable ZS, and Q was the symbol reserved for this. This is the overall block diagram, and what is the exercise now we are going to take up? We are going to take up the physical subsystems corresponding to all these block diagrams, getting the mathematical models of those subsystems, and then giving you a feel as to what type of industrial control systems are in use. This is the overall situation we are going to take up now. Now, I think at this point, if you agree with me, the total design will depend upon the feedback loop. You won't mind if in my discussion I do not include this indirectly controlled variable, because after all the indirectly controlled variable is just a hardware component in the overall system. It does not enter into the design of feedback control system, this being outside the feedback loop. So, I can take y, the controlled variable, as the signal of interest to me. If q is the signal you are interested in that particular case, you will design a suitable hardware so that from y a variable q can be suitably controlled. So, as far as the feedback control system is concerned, there is no problem. You can simply forget about q and you can concentrate about the controlled variable y. This is one point I like to make. Another point I like to make is the following. You will please note that E cap, the cap is to be explained. Why did I use the cap? Why not the E signal? The reason being this, that as far as this this signal is concerned, it is the comparison of the reference signal with the feedback signal. The feedback signal is coming after sensing of the controlled variable y. This is the controlled variable, this is the sensor. So, it means this B is not equal to y. I will call the error signal E is equal to y minus yr. See the difference between E cap and E. This E I call as the system error signal, and E cap I name it as the actuating error signal. Why do I call it the actuating error signal? Because this is effectively the signal which is entering the loop, which is the input to your controller, which is exciting the brain of the control system. You will please note, E cap is the signal which is exciting the brain of the system, while what is E? E is the signal really you want to make it 0, because E is the error between the controlled variable y and the commanded signal yr. This error signal has to be reduced to 0. So, there is an E and E cap may be different signals, it depends upon the transfer functions AS and HS which I am going to use in particular control situation. So, this difference between the two symbols E cap and E should be clear, please. If this is okay, in that particular case, now I will say that the standard diagram of interest to me will be the following. I can skip S if you do not mind, to save time, to save space, but surely all these are in the Laplace domain. This becomes the standard diagram for me, please. This is the command, this let me name it again, because I will be interested in this signal. This signal is E cap and this is y. For the feedback design purposes, I am going to work with this type of block diagram. This is the feedback loop which has got the controller transfer function, the actuator transfer function, the plant transfer function and the sensor transfer function in the loop. Okay? Now, for the convenience of analysis and design, well, it may be possible to see, please see that it may be required to manipulate this particular block diagram into more convenient form. I need your help here. In this particular case, I simply want to get this particular transfer function in this form, and help me whether you accept this. See the question, my point is this, that the block diagram may be manipulated to write it in some more convenient form, the convenience to be studied with respect to the requirements of analysis and design of control systems. This is your D here, this is GA here, I am removing this particular block, this is GP here, I put a summing block here plus plus and a transfer function n here, a w here and y, and this is the h. You see an interesting point. I make this change. The claim is this, or I feel that this will turn out to be more convenient than the block diagram I have already drawn. The block diagram I have already drawn is just in front of you. What is there? In this particular case you will note that the transfer function between w and y is gp. In this case the transfer function between w and y is gp, and the transfer function between u and y is ga into gp. Look at this block diagram please. The u is here, the transfer function between u and y is ga into gp, and if I make this n appropriately equal to gp, in that particular case there is no harm in taking this n separately, because I know that the transfer function between y and w in this particular case should remain as the case in the earlier slide. I hope you are getting my point. So you see that if in the two cases I can make the transfer function between y and w the same, it really does not matter whether the summing junction is shown at this point or at this point. Whether the summing junction is shown at this point or at this point, it is one and the same thing. And what I do now, that this GA and GP can be clubbed together and I call it as a plant transfer function G. So a more convenient block diagram now I am going to write is the following: A plus minus D, a single block G plus plus Y, and let me put a block N, and this is your W and here is H. Definitely you see your OK is required to understand this manipulation. What I have simply done is this, that if U is this signal over here, the two block diagrams will definitely be equivalent if between y and u you have the same transfer function as in the original diagram. In this case it is G, which is equal to GA into GP, and as far as the transfer function between y and w is concerned, in this case it is N, which is same as GP, and therefore this particular block diagram is equivalent to the block diagram I have drawn over here. This point must be very well understood. Block diagram is nothing but a symbolic way of manipulating the system equations, and as you will find in control system setting, it becomes more convenient to work with block diagram than to work with basically the system equations. So this manipulation, you will really be tuned to these manipulations, because it is nothing but rewriting the block diagrams with this particular point in mind, that the system equations in the two cases should be identical. This is what I have done. I claim that the transfer function between y and u and the transfer function between y and w in this block diagram is identical to the one I have given you earlier, and hence the two block diagrams are similar or same. Okay? I hope this is okay. Now if this is okay, then a question comes to you. So in this case now you manipulate the block diagram for me so that this A block does not appear in the forward path. I want you to solve this question. This A block need not appear in the forward path. Just to give you a trick, to give you the clue, I may say that this point E cap should have the same value in the present case and in the case you are going to change. Now in this particular case E cap, please help me, you get from here is AYR minus HY. This is your E cap. If your E cap, rather from here I can write even U is equal to DAYR minus DHY. This is your U signal, the control signal in this particular block diagram. Okay, please see this now. I take this plus minus A into D I put over here, this is G, a block here and an N here, W, this is Y, and H by A here. Please see whether it is equivalent. You just look at U, whether it is equivalent or not. U equal to, this is your YR, U equal to ADYR minus H by A into A dy, you find that it is equivalent. H by A block is being multiplied, it is a cascaded. As I told that the two blocks in cascade, their transfer functions will be multiplied. The only thing is S variable I am not writing to save space. So, if I go from y to u, you find that it is this particular loop h by a into a d gives you h into d into y, and your earlier u variable was d-a-y-r minus d-h-y. Now, you have the same u variable, and hence this block diagram and this block diagram are equivalent. In this particular case, you find that the input does not have the reference. Now, you see, I at this juncture I will not tell you as to what convenience are we drawing from this particular manipulation, but it should be clear that manipulating the block diagram may be required in control system analysis and design for the purpose of convenience, and manipulating a block diagram is nothing but manipulating the corresponding system equations. Okay. You find that the two blocks are equivalent, where in this particular case YR has turned out to be an input signal to this, which you can say in this particular case is a reference input R if there are no reference elements. Okay. It means the reference element block has been taken inside the loop now, and this becomes the total loop where A also appears. Okay. Now, if by design or by chance H happens to be equal to A, please help me, what will be the situation? It may be by design, that is your sensor transfer function can be equal to the transfer function of the feedback elements. If H happens to be equal to A, in that particular case the block diagram appears like this: YR equal to R. A into D, G plus plus N W Y. Just see, very important diagram, it has a meaning, because many a system, many a times you are able to transform your system into this block diagram, and the statement which I make here, an important statement, that this block diagram is quite convenient from the point of view of design. Okay. This block diagram, as is visible from the structure, is referred to as unity feedback system. I really need your attention on this statement. Many a times this causes confusion, that if you are working with this type of block diagram, one gets the feeling as if in this particular case Y is directly coming here and going to the summing junction without a sensor in between, or necessarily the sensor transfer function is equal to 1, because it appears that way. If I give you this block diagram, it appears as if this corresponds to a system with sensor transfer function is equal to 1. Please see, it is not the case, it need not be the case. Your sensor transfer function need not be equal to 1. You have already seen that in this particular block diagram has been obtained by a sensor transfer function H is equal to the transfer function of the reference elements. Still your the overall block diagram has turned out to be into what is called a unity feedback system. So a unity feedback block diagram will come very often in our discussion, and you will always keep this in mind, that the result or this diagram has been obtained by manipulating the original block diagram. This particular block diagram necessarily does not mean that the sensor transfer function is equal to 1, though it does not rule out that possibility. Your sensor transfer function can be 1. What I mean to say is that it is not necessarily equal to 1. Okay. So this type of manipulation also may be required. Yes, please.
Why don't we club AD and G also?
Okay. This is what I was going to do in the next slide. Yes, I definitely agree with you. I now say that with all these manipulations, as has been suggested by him, I can come to now this diagram which represents the system equations, and this diagram is R, the reference input. This now becomes the diagram which I am going to extensively use for design. Please see, plus a minus sign here, I am putting minus sign decidedly because mostly our structure is going to be a negative feedback structure. Here now, as has been suggested by him, let me call this as the transfer function D. Again please see, now this D is the block for the transfer functions in the forward path which have come after manipulation. This need not be the transfer function of only the controller, okay. This need not be the transfer function of only the controller. However, in my block diagram there should not be any confusion if I put a controller as the major contributor to this particular block. But like A was multiplied in the earlier block, this may be the result of suitable manipulation of the block diagram as well. But to give you a general configuration of the diagram on which I am going to base my analysis and design methods, I will take this D as a controller transfer function, with the statement which I have overemphasized that all these blocks should not have one-to-one tie-up with the physical elements. All these blocks have resulted because of the manipulations of the basic equations of the system, okay. Similarly, now I put another block over here and I call it as GS, and let me call this as plant. The total thing I am clubbing, the actuator, the power element of the system has also been clubbed into this GS, and this total I call it as G, and this I reserve as the terminology for this. And here is the controlled variable Y, this variable let me call as U. This Y is being taken from here. This is the block, let me use HS for this, this I say is the sensor transfer function. Now, or let me call it a feedback path element, because I am again repeating, this need not be the transfer function of only the sensor. It may be the result of manipulation. Some elements, the reference elements may also be coming into this particular block. Sensor I am using, but again it could be an H block which may be coming as a result of the overall manipulation of the system equations. This let me say is your feedback path elements, the feedback signal, and this, help me please, should I take E here or E cap here in this particular block diagram? If I am taking this block diagram as per my terminology, what signal should I take, E here or E cap? I think it is clear it should be E cap, because E by definition is the difference, is the system error, is the difference between the actual signal and the commanded signal. It is between Y and YR. You will please note the YR is not even shown in this particular block diagram. It is R, the reference signal. It means R has been generated from YR. Since the feedback loop does not directly involve YR, I need not include in my basic feedback loop transfer function model, but it should be very clear to you, when you are analyzing the total performance of the system, you should calculate the error E between Y and YR, which is not visible in this particular block diagram. The error E cap is simply an actuating error signal which is going into this particular controller. YR specifically we need not show in our design diagram in our feedback loop, because this particular point or that particular block, it is not entering into the loop, which is the basic design element as far as our total effort is concerned, okay. Yes, please.
There is no disturbance.
Yes, I am not completing. You are very right. I am sorry. Yes, I should have shown over a block over here. I had in mind, I had to complete it. This you consider, disturbance is a very important component. Without disturbance, a control system block diagram has no sense at all, because you will recall I have made a statement, if there were no disturbances in the system, there would have been no course called feedback control theory, because the open loop control system could have taken care of all other requirements very well. So, disturbance I am definitely taking care of by this plus and plus. I am adding a plus sign over here. Again, this could be minus, the disturbance can have an additive effect or the opposite effect, but symbolically let me represent it as plus, and here I am going to put a transfer function NS, and here is my disturbance variable W. This becomes the overall block diagram I will be working with. Yes, please.
Is in this DS the reference element into the actual controller D into A.
This B,
DS.
DS is the actuating error signal, into D is the controller signal U. What is your question? Please repeat your question.
So isn't the DS D into A?
Yes, this is what I said, that I think it should have been clear. DS is the total transfer function between U and E cap. These are the variables, and controller I am just putting over here just because this will represent that any action which generates a control signal U from the actuating error signal E cap is represented by DS. Now don't relate it to A. Yes, in a particular transfer function, if a block diagram has been manipulated that way that A has been taken inside the loop, yes, this DS includes that as well. Now I am giving you the overall block diagram, that is all those elements between U and E cap will be clubbed into a single transfer function called DS. This block diagram is now not a carryover of the earlier block diagram, please. I am just summarizing the overall discussion that all those elements which contribute to a relationship between the control variable U and the actuating error signal E cap will be clubbed into a single block, and that single block I am naming as DS. Yes, if you refer to the original diagram, this DS with respect to the original diagram is A into D. You are very right in that sense. Is it okay, please?
So if it's A into D, then instead of E cap it should be E, because the input is YR then.
Okay, let me take this particular diagram. Just look at this particular block diagram. It's not E cap here. It will become E only when H is equal to A. Only when H is equal to A it will become E. Consider this particular block diagram. This is E cap, because in this particular case Y through H by A, when A, the reference elements have been taken in this particular sense, Y multiplied by H by A is your B signal, and R minus B is the actuating error signal which is going into A into D, and hence it is U over here. Okay. So now you see this point, that if you give reference to this block diagram, I need your attention because I like to answer your question, so there should not be any confusion. Though D is used here and D is used in my final block diagram also, but now what I am doing is the following. All those elements which contribute to a relationship between U and E cap is clubbed into a single block, and I am naming it as controller transfer function DS. Okay. Any transfer function which is representing the relationship between output this Y and B, I am taking it as the transfer function HS, and the relationship between the control signal U and Y as the transfer function GS, relationship between W and Y as the transfer function NS. Now the physical elements, or how did we manipulate this equation, the original transfer function, that should not confuse us now. This from now onwards will become our standard terminology. The original diagram was given to you to convey to you that these blocks need not represent the basic physical elements of the system. They simply represent the mathematical relationship or dynamical relationships in the system. Okay. So here D, G, N and H, we should not try to relate to the physical elements immediately. Still I have given the names, because many times it is possible to relate, and secondly, if we have some names, it becomes more easier to visualize the total working of the system. Okay. So these D, G, H and N are the basic blocks which represent the dynamical relationships. Whatever systems are coming into the picture, all the systems should be taken into consideration to get these dynamical relationships and hence the corresponding transfer functions. Is it okay, please? Now in this particular case itself, if I have a diagram in which HS is equal to 1, in that particular case I will refer to that system as a unity feedback system. Yes, in that case, okay, let me redraw it. Since you have raised a question, I will redraw this. For a unity feedback system, I think I can give you this diagram now, plus minus, this is your DS, this is GS, here now let me put NS, and here it is W, this is Y. You are very right if you say that now you put an E. Because in this particular case now, whatever be the manipulation, in this particular case the feedback y as per this equation model. Now you again I said do not think that h is necessarily equal to 1, but finally D, G, N and all these blocks have been obtained by manipulation of the system equations in such a way that this becomes the mathematical representation in the block diagram form. In this case y is going, your yr will be equal to r, the reference input. Since y is being compared with yr, this particular signal is system error signal. So in this case the actuating error E cap is equal to system error itself, which is equal to yr minus y. So in a unity feedback structure, the system error E explicitly shows up in the block diagram, but if it is a non-unity feedback structure, that is if you have H in the feedback path, in that particular case E cannot explicitly appear, it is going to be E cap, the actuating error signal, which will appear in the diagram. And one thing I can assure you, that even if there is a gap at this particular stage to understand these diagrams, when we come to the physical systems, you will find that well, a suitable interconnection of various elements of a physical system you will be able to translate into one of these two basic block diagrams. And from there, even if there are some gaps now, I am sure those gaps will be filled up when we come to modeling of physical systems and transforming their block diagrams into one of these standard block diagrams. This is sure, for my design purposes I will pick up these two standard block diagrams only always. Okay? I hope this is okay. Yes.
Why is yr equal to r?
yr equal to r. Okay? For that I will like you to go to this particular block diagram. What is yr? yr is the command signal. Let us say your command signal is temperature, okay, physically. A, it is converting it into a voltage. So r in this particular case is a voltage signal. So as far as the physical variables are concerned, if all these blocks represent physical quantities and variables, in that particular case yr is temperature, A is a block here and r is the volt. Now if I transform this particular block diagram, that is there may be a situation that in this particular case your y, the variable here is also a temperature, this temperature is also getting transformed into voltage. So volt here, volt here. Now if this A is taken inside, in that particular case, as far as mathematical representation is concerned, the mathematical representation of the two will be equivalent if I make yr equal to r. You can just write the equations. I said the two mathematical equations will be equivalent, that is the system equations obtained from here. Now physically it will not make any sense. That is why I said that neither the variables nor the blocks after manipulations should be given a physical interrelationship. So physically it will not make any sense, but you write the mathematical equations from this block diagram, or you write your mathematical equations from, let us say, this block diagram we have written, you will find that the two equations are exactly identical, and hence in this particular case we can mathematically represent a block diagram this way. Okay? And it is this way only that the final situation has been taken to one of these two block diagrams. One is a non-unity feedback system and the other is a unity feedback system. Okay? Is it okay, please? Before I conclude this discussion, I will like you to get this basic block here. Let us say r plus minus I have taken E cap d g plus plus n w y h. If you know through any other course, can you tell me directly what is ys over rs equal to? Ys over rs, the closed loop transfer function of the system. What is this equal to if I if I am interested in the overall transfer function? First of all, please see, it is a 2 input 1 output system. In a 2 input 1 output system, if you are interested in a transfer function, naturally superposition will have to be applied. You will have to take one input at a time. So I consider the situation where w is taken equal to 0. and I am interested in a transfer function between y and r. Please help me if you recall. ds gs over 1 plus ds gs hs. I hope I can assume it, I need not go for the derivation. Is it okay please? And please see that if this is a plus sign here, that is if you have a positive feedback loop, in that particular case this will become a minus sign here. This is a basic loop, and I may call this transfer function as a reference transfer function, because this relates the output variable y to the reference variable r. I call this as a reference transfer function. You have rightly given this transfer function to me. Now please help me if you can manipulate the transfer function between y and w. Between y and w, now you set r equal to 0. So I am interested in this particular situation now, setting r equal to 0. So this is a minus sign here, I have a signal d, this signal e cap, this is d here, g here, a summing point n w y h. Yes please, I want you to give me the transfer function between y and w. So it is ys over ws setting rs equal to 0. N minus ns, if you say, then I think making an error. 1 plus, I think there are some errors in all the answers, so we can have a quick look at this particular diagram and derive. This minus, I take it into this a single minus 1, and let me complete the loop this way. That is the error detector I am removing and putting it as minus 1 here. So it means the transfer function now becomes d, the block diagram now becomes dg plus n w e cap, let me put a minus 1 here, and this is your h. Okay, the basic equations, E cap s equal to minus h s into y s. The other equation, let me write between y and E cap. Between y and E cap, I write y s equal to d s g s E cap s plus n s w s. These are the two equations. Eliminate your E cap. Okay. From these two equations, if you eliminate your E cap, now you can see some of you might have given the right answer, I do not know. If you eliminate your E cap, now it becomes y s is equal to minus d s g s h s y s plus n s w s, and therefore your y s over w s with r equal to 0 becomes equal to n s divided by 1 plus ds gs hs. Numerator is n s, denominator is 1 plus ds gs hs. You will note one point, that in the two transfer functions, one you call it reference transfer function and the other one you call it disturbance transfer function, the denominator is the same. It is 1 plus ds gs hs. This is, as you can easily visualize, is the loop transfer function, because it is the multiplication or cascading of the transfer functions in the loop. ds gs hs is the loop transfer function, and in this particular case I can just, in this particular case, a symbol I will give you, or a, in the disturbance transfer function now onwards I will represent by MWS, and the earlier transfer function which you had given to me, this transfer function, let me reserve MS for it. So it means MS is my reference transfer function, MWS is the disturbance transfer function. In terms of these two transfer functions, I conclude my discussion with this particular block diagram that your input is Rs. This is the Ms transfer function, and here let me put a disturbance transfer function MWS. Here is my disturbance variable Ws and this is Y. This is the equivalent block diagram I have got. For the purpose of analysis, I will require this particular block diagram because this block diagram gives you a direct relationship between the output and the reference element and between the output and the disturbance element. So, this is the equivalent block diagram of the standard block diagram we have reserved for design. Thank you very much.